Okay, everybody good on structural equation models, standardized and generalized structural equation models? Any questions? Okay. Okay, new topic. So that's all we're going to do about building models that you can generate data from for right now. Now we're going to begin the process of going the other way. And the first topic to do with that is how to estimate the parameters of a model from data, right? So what I've shown on the screen so far, right, is a picture where I've built a graph, I've built a parametric model based on that graph, I've built an instantiated model based on that parametric model, and I've generated data. And now, one of the boxes on that left palette is estimator. And so I've put that estimator onto the workbench, but I haven't connected it to anybody. So my question to you is, now that you sort of got your head around the ontology of these different pieces, which of the blue boxes should have inputs into the estimator? Data. Everybody agrees you need data to estimate. Is that it? And a parametric model. That's right. And why is that? Because basically, the parametric model defines the parameters, right, that you're going to estimate, but doesn't specify their values. The instantiated model specifies their values. There's nothing to estimate. They're already in there. And so what an estimator really is doing is taking a parametric model and data and then searching over the parameters to minimize some loss function or to maximize some likelihood function. That's essentially what it's doing. Okay. So now I'm going to go demo something, and then I'm going to ask you to follow along and do the same thing in a minute. But now it's going to get fun. Okay, so I have this model, right, which is a parametric model, but I'm going to delete it, and I'm going to use this model, which is a non-standardized model, but it's just fine, right? And if you can read it, the parameters say 0.5, 0.6, and 0.7, right? And those represent the strengths of the causal influences, right, from x1 to x3, x2 to x3, and x2 to x4. So what this means in causal terms representationally, for example, if I look at this parameter 0.6, that says that no matter what x1 is, because this is a linear model, if I intervene to change x2 by 1 unit, what should I see? I should see a change in the expectation of x3 of 0.6. And I should see a change in the expectation of x4 of 0.7. So that's telling me in very direct terms what's the result of an intervention by changing the variable by 1 unit. Right? And that's the typical, right, interpretation of these coefficients. Okay? So presumably, if I had enough knowledge to specify the structure of this model but not know the actual values of these parameters, but I had data, then I could get the actual values of these parameters estimated for me. So that's what I'm going to do. Oops. Okay. So I put an estimator on the workbench, and I say to the estimator, go ahead and estimate. All you have to do to estimate a model, right, is double click it. And up it comes. Okay. So you can see I just generated data, right, and I don't know what that data is, and the estimator is going to give me, right, a bunch of values. So let's compare the values in the instantiated model from which the data was actually drawn to the estimated values of the parameters. So what you can see is that the true value of this parameter is x1 to x3, 0.5, and the estimated value is 0.5243. Pretty close, right? And this one is 0.6, and that one is 0.5744, also pretty close. And this was 0.7, and that one's 0.67. So they're all within like 0.03, which is kind of what you'd expect from a large sample size of 1,000 sample points, okay? So that's getting parameter estimates. It's that simple. Now, when you're doing science, what you usually do is, if I estimate the parameters of a model, I want to also then do inference, right, which will tell me confidence intervals around those parameter estimates, hypothesis tests based on that, et cetera, et cetera. So there's two ways to get that information in tetrad. The quick and dirty way is just to roll your mouse over the parameter. So if I look at that 0.5243 and I get the blue thing underneath it, it says the standard error is 0.0220, the t-statistic is 23.78, and the p-value is 0.000. That's one way to get that information. Another way is to say tabular editor. And that has all the parameters that are going to be estimated. And the one that I'm just looking at is the x1, x3. So that's that edge, that's that row there. And that gives me the same information, but I can look at it carefully. Okay? Now let me ask you a question. What does that p equal 0.000 tell me? What does it say? What does it represent? What's that inferential statistic mean? See, this is like statistics 101, your nightmare. What?
Highly significant.
Highly significant. So if you had to put it in probability terms, what's that the probability of?
Probability of getting the data that you got given the model specification that you have.
That what?
So
You're close. So that means that if the model, right, is correctly specified, and I sampled again and again and again, right, the probability that I'd estimate a coefficient this big or bigger, given that the real coefficient was 0, is 0. So the hypothesis, the null hypothesis is that that coefficient is actually 0 in the world. Yeah?
Can you change that statistical test to non-parametric?
I could not, but can we change that to a non-parametric test? If we had the formula, we probably could. And if you wanted to, yeah, you certainly could. Yeah. So one of the things we'll get to in the next couple of days is a command line version of tetrad, so you can go and actually fill with much more deep parts of the algorithms and et cetera. So if you wanted to do a non-parametric test here, you could. Okay, but what that means, that 0, right, and what this point, right, what this 0.6295 means is that the null hypothesis is that that coefficient, that parameter estimate, right, is in the population 0, and that assuming everything else in the model is what we think it is, what's the probability we would actually estimate that big or bigger, right, if we kept sampling and sampling and sampling and sampling. So the p-value of 0 says we can reject the null, right, of the coefficient 0. Okay, so what is that coefficient? x1 to x3. So we might want to interpret that as saying we can reject the null hypothesis that x1 has no influence on x3. That's what we really want to do. Right? And that's what we're after. Okay. Now, the next piece is what might we be able to tell about the model and how it fits the data, and how is that different from the coefficients and how they look significant or not. Okay? So let me take you now into one more statistic and then go back to the slides, and then I'll go back and we'll do something more interactive. So on the tab on the estimator, right, is a thing called model statistics. And if I click on it, I get all this information. I get the degrees of freedom equals 3. I get a chi-square of 2.1433. I get a p-value of 0.54, and I get a BIC score, a CFI, and RMSEA. What do all those things mean? What does the p-value mean here? It's a little different idea, and it's very important to get your head around this, because it's a different idea. This means, right, that the probability that the chi-square is that big or bigger, given the model is correctly specified, not the null, right, is 0.54. So this model cannot be rejected by the data. So in model fit, the idea of the null hypothesis is flipped. The null hypothesis means the model is correctly specified. And in the coefficient inference, the null hypothesis is the coefficient 0. So you're trying to reject the 0 to get to significance. In the model fit, you're trying to not reject the model so you can make sure the model is unrejectable. So it's a flipped idea. Okay? And it's very difficult to keep that in your head. So don't expect to. I couldn't for years. Yeah?
Does that include which direction causation flows? Is that testing for that specifically?
I'm going to get to that extremely carefully. So hold on for a minute or two. Yeah?
Just going back a little bit, when you generate data from your model, is there a way you can set the seed for that?
Set the random seed?
Yeah.
Yes, if you go to the command line.
Okay.
Yeah, which is a great question because you really oftentimes want to have that happen. Okay, now I'm going to go back to the slides and I'm going to make all this vivid because this is now we're getting to the nub of it.
You didn't allude to the RMSEA that hasn't been calculated here.
I'm sorry?
The root mean squared error hasn't been calculated. Why?
I don't know why that's not calculated. Do you have an idea in that case?
Calculated too.
I don't know why that's not, that usually should be calculated.
It is a very important model fitness parameter.
Yes, it's another model fit statistic along with the p-value, the BIC, the CFI, and in typical structural equation models you also get the root mean squared error. Okay, let me go back to the slides. Okay, so I showed you this, and then I showed you this. Now, up at the top, right, I'm going to talk a few minutes about coefficient versus model fit inference. So the coefficient inference, the null hypothesis is coefficient equals 0, right? So the beta 1, 3, right, equals 0 might be our null, and then the p-value is the probability that the estimated value, which is represented by that beta 1, 3 with a hat over it, right, that represents the estimate. So the probability is the estimated value of the estimate is bigger than or equal to what it actually came out to be, given that it's actually equal to 0. The population thing is equal to 0. And what I put in red, the rest of the model is correct, which is totally crucial. Okay, so we reject the null, and we say the coefficient is significant when the p-value is less than alpha, and alpha is usually set to 0.05 for publication purposes. Okay. And there's a lot of controversy over that, and I don't want to get into that at all. Okay. So, right, that little 0.5 there in the true model, right, and there's the estimate of 0.4788, and the p-value is 0, etc. Now, the model fit, right, this is a different set of values, but the idea is the same. The model fit, the null hypothesis is the model is correctly specified. What that ends up meaning that it in turn really matters is the constraints that the model entails to hold in the population, right, are all actually in the population. And I'll get more to that in a minute. So what does that translate to? The p-value for the model fit is the probability, right, that the deviation between the estimated maximum likelihood covariance implied matrix and the sample covariance matrix. That means the difference between how we estimate the implied covariances for the model and what we observe in the covariance matrix, right? The probability of that deviation is bigger, right, than the chi-square, which is the measure of that deviance, 5.7137, given the model is correctly specified. So the essence of it is really simple, right? The model, after you estimate the parameters, makes a prediction about the implied covariance matrix. It says, here's what I think the covariance matrix is, right? And then you look at how closely that deviates from what you observed in the sample. And then if they're really, really different, but they should be pretty close, kick that model out. And if they're different, but you could expect that kind of difference because of the statistical variation you would expect, then you can't reject the model. So it's all a question of, can we compose a reference distribution to say how much difference ought there to be, on average in some way, between what the model implies and what the sample looks like. And where that actual difference comes from is the next topic, and we're going to get into that in a little bit of excruciating detail. So put your thinking caps on right here. Okay, so here are the 4 boxes, right? On the top is the coefficient, right, and the model fit. And if I have the null hypothesis that the coefficient is equal to 0, right, and the p-value is below 0.5, then I can reject it, right, and therefore reject the coefficients being 0. It's a significant edge. And if I can't reject it, it's an insignificant edge. It might be 0. Can't tell. In the model, if the p-value is below 0.05, then I can reject the correct specification. Then the model is not correctly specified. I can throw the model out. So if the model fit statistic says below 0.05, forget about it. Model's bad. And if the model is above 0.05, then I cannot reject the correct specification, right? The model may be correctly specified, and it may not. There may be an alternative model that has the same fit. Okay? So what is model fit all about? So suppose the specified model is just this simple x1 causes x2 causes x3, and the true model is exactly that same causal structure. And the true coefficients are 0.6 and 0.5. Now, because this is the true model, I can derive the true correlation matrix that this model entails, right, in the population. And without going into the detail, because these are standardized models, right, x1, x2, which is right here, is 0.6, that's 0.6. x2 and x3 is 0.5, that's 0.5. And x1 and x3 is the product of this times this. 0.6 times 0.5, which is 0.3, right there. When I estimate the parameters of this model, here's what I'm actually constrained to be estimating by the implied covariance matrix. So the population, beta 1, will actually be the only thing governing the x1, x2 correlation. Beta 2 will be governing the x2, x3 correlation. And then I don't have a third parameter to do the x1, x3 correlation. I only have 2 parameters to work with. And it turns out in this model that the implied covariance matrix is beta 1 times beta 2. So you have 3 numbers to fit and only 2 parameters to do it. That's why you might be off. That's the constraint this model entails. It only gives you 2 parameters to fit 3 numbers. If you're lucky, you can do all 3 numbers with the 3. But the basics of it are, the estimate for beta 1 is going to be the sample covariance of x1 and x2, which is probably going to be around 0.6 because this is the model. The estimate for beta 2 is going to be the sample covariance for x2 and x3, which is going to be approximately 0.5. And the estimate for beta 1 times beta 2 is completely constrained. You can't do a number. It's going to be about 0.3, which is going to be your estimate for the population correlation of x1 and x3. So this is all good. So far, so good. Now suppose that the true model has x1 causing x2 with 0.6, x2 causing x3, but x1 also causes x3 with a coefficient of 0.2. So that's the true model. But this is the model you specify and estimate. Your model is wrong. How do you know it's wrong? What's the model fit that tells you you're wrong? Okay, so we go into the same kind of detail, right? The x1, x2 is going to be 0.6. The x2 and x3 is going to be 0.5. Actually, that's wrong. Forget about that for a second. And the x1 and x3 is going to be 0.3 plus 0.2, which is 0.5. So that's the approximate true model population covariance matrix. And again, this is the implied covariance matrix in the specified model. So if I gave you all day, and I said, you get to pick beta 1, you get to pick beta 2, to try to recover these numbers, you couldn't do it. Why? Because beta 1 times beta 2 is what you're going to use to predict the x1, x3, right? And 0.6 and 0.5 will recover these guys, but then it'll make this be 0.3, but it's actually 0.5. You'll be off by 0.2. So you might say, oh, okay, let's adjust these two to make this be 0.5, but then this is going to be wrong, or this is going to be wrong, or both. So you're screwed somewhere. You cannot recover these three numbers with these two parameters. There's absolutely no way. And that fact, the fact that this correlation is the product of these two parameters, is the constraint you're under. So this model implies 1 degree of freedom, which is completely misnamed. It should be 1 degree of constraint. The more degrees of freedom, the more degrees of constraint. So degrees of freedom are actually degrees of constraint. I don't know why they're called degrees of freedom. No idea the history of that. It's the most misleading name you can ever have. It's exactly the wrong name. Okay? So when I'm looking at whether the model fits, I'm saying, okay, I'm going to be off. I know I'm going to be off a little. How far am I off? Because the sample is never going to be exactly the population. And what I'm actually testing is that constraint, right, and seeing if it's reasonably close to being satisfied in the sample, or is it way, way the hell off? Okay. So the model fit, model's correctly specified, the constraints are true. In this case, the constraint for this model is that the correlation of x1 and x3 equals the correlation of x1, x2 times the correlation of x2, x3. That's the constraint this model entails. Cannot get around that. There's nothing you can do. And then the question is, right, when I look at the deviation between the implied covariance matrix when I estimate and what I actually observe in the sample, right, how big is it? Well, this chi-squared is the one number that expresses the deviation between my estimated covariance matrix and my measured sample covariance matrix. That one number is the total deviation. And it's constructed precisely so that its distribution will be a chi-square, with the degrees of freedom equal to the degrees of constraint in that model. That's how it's constructed. That's why it's constructed, so we can do that inference. Okay. That's a lot to get in your head, but you get the basic idea? So we're always testing, and this is the key of it, these models entail these constraints, and it doesn't matter the parameter values. Those constraints are impossible to avoid if I specify a model. And that's what I'm testing when I look at the model fit. Okay. Now I'm going to get to the fun part. Okay. So I've done this model, and I've estimated the true parametric model. And in an estimator, right, I have inferences about the individual coefficients, and I got this model statistic, which is the p-value is 0.5432. In this case, there are 3 degrees of constraint. The chi-square was 2.1, which is lower than the degrees of constraint. And so what you really expect probabilistically is that the degrees of constraint will equal the chi-square. And if the degrees of constraint are much lower than the chi-square, and the chi-square is really big, right, then there's too much deviation. The model is rejectable. That's the statistic. In this case, it's not. All right. Now suppose, right, I take this graph and I switch it. So I say, let's take the edge that goes from x2 and x4, and let's switch it so that it's now going from x4 to x2, leave everything else the same. Right? Parameterize that, so I have now the x4, x2, so beta 1 now measures that. And now I say, okay, let's do an estimator. Let's put the data in from that. So now what you're looking at is the parametric model that I'm estimating is wrong. It's the wrong model by one edge. I flipped the edge. The data came from the model that you originally saw, and I'm going to estimate the parameters of the wrong model. What will I see? Let's compare this to when I estimated the true parametric model. Okay, so if you can't see that in the back, I'll read it. So the edge from x1 to x3 was estimated at 0.5243. In the new model, it's also 0.5243. The x2, x3 was 0.57. It's also 0.57. And in the original model, the x2, x4 was 0.67. And now from x4 to x2 is 0.32. Right? So what we're seeing is everything's the same except for that flipped edge. And that's quite a different value. And of course, when you really think about it causally, right, what this says is that x4 has no influence on x2 at all. And this says that x2 has no influence on x4 at all. So they're very different in their claims. What could I learn from the coefficients and whether they're actually appropriately 0 or not? Well, this coefficient had a p-value of 0. That coefficient has a p-value of 0. So I cannot learn anything about whether or not x4 causes x2 from the coefficient inference. So maybe I can learn it from the model fit. They're the same fit. Exactly the same fit. So 2.1433, 2.1433, the p-values are the same. Those two models fit the data exactly the same. There's nothing I could do to tell this apart, one model from the other. So I cannot distinguish whether x2 causes x4 or x4 causes x2 from the data here. Nothing I could do. So to presume I could would be, right, hubris. Now, let's do the same thing, but instead of flipping the x4 edge, let's flip the x1, x3 edge. So I have two edges, I keep the same, and I flip one of them. Oops. All right, so true parametric model. This parametric model is the true one with one edge flipped, and this one is the true one with a different edge flipped. Now what do I see? Okay, so here the edge is flipped, the p-value is still 0, so the coefficient of that edge is highly significant, and this is high, and these are the same. But now look at the model statistics. This is where the rubber hits the road. So I'm going to read it to you so you can really get this in your head. So the true model and the one edge flip that is equivalent to the true model, 3 degrees of freedom, chi-square of 2.143, p-value of 0.54. The model in which I flip a different edge, so it's no longer an equivalent model, has 3 degrees of freedom and a chi-square of 127. The p-value is 0. So in one case, a one edge flip, completely the same equivalent model. And the other case, a one edge flip, absolutely disaster. The whole thing falls apart. The model is completely rejectable. Okay? So we can tell from the model fit statistics, right, that this one, right, fits the data. We don't know if it's the true model, but it fits the data. And we can tell this one does not fit the data and is rejectable. So I think the basic rule of thumb is that if you're trying to actually make inference about causation, you want to know what of these arrows, right, you could actually distinguish from the data and which are embedded in a model that as a whole model seems to fit the data reasonably well. Okay. Now, it turns out that I could win money in a bar by giving you a model and saying you get to make a one-edge flip anywhere in the model you want, and I can tell you whether it's an equivalent model, right? Because it's an easy theory to apply, and I'll teach it to you tomorrow, right? You probably can't do that yet unless you're more advanced than I thought you are. But what you'll learn tomorrow is that if I tell you what the one-edge flip is, right, split second later you can say, oh, that's going to be the same fit, it's an equivalent model. I didn't change, right, out of a different equivalence class. Or if I make a one-edge flip, oh no, that's not equivalent anymore, right? So you'll be able to do that tomorrow without any question whatsoever. For now, I want you to go ahead and I want you to actually do something of the sort I've done so you can get your head around the fact that, right, when you estimate alternative models, you can tell something about whether they're true or not by the fit, but you cannot tell anything from the coefficient significance, which is when you think about the way research is done and published, it's all coefficient significance, right? And this is a big pet peeve of mine, right? Because when you see coefficients reported in their inference statistically, right, and the p-values both, it doesn't mean anything causally, because the model might be wrong. So you need something about the model as a whole, and that's what we give you. Okay, so now go ahead and do this, or play with whatever you want to do something like this so you can test how the model fit and how the coefficient statistics look and when you have equivalent models and when you don't. And then, we'll walk around and help. When you're done, right, we'll take a 10 or 15 minute break. So we'll reconvene and I'll start again at 3 o'clock. Okay? Any questions? Yes, that's cool, yeah? Good. Okay.